Welcome back to the Deep Dive. Today we're jumping back into the online encyclopedia of integer sequences, the AEIS. It really is just an amazing resource for anyone interested in number patterns.
Oh, absolutely. It's like a map for the world of sequences. You find connections you'd never expect. Really invaluable.
And today we're zooming in on one specific sequence, A000235. Now this one counts the number of rooted trees with n nodes that have a height of exactly 3.
Mm-hmm.
So maybe we should quickly recap what a rooted tree is for listeners who might be newer to this. They're basically these hierarchical structures, right? Like an org chart or a family tree.
Precisely. You have a special node, the root, at the top, level 0, you could say.
And everything branches out from there. Parent-child relationship.
Exactly. And that structure gives us concepts like depth, how many steps you are away from the root, and crucially for today, height.
Which is the maximum depth in the tree, the longest path from the root to the furthest leaf node.
That's the one. The longest path down to any leaf. And for A000235, we're laser focused on trees where that longest path has exactly 3 edges. Not 2, not 4, just 3.
Okay. And why is counting these specific trees important? I know tree enumeration is big in combinatorics and computer science.
It really is. Think about data structures, how networks are organized. These tree structures are everywhere, often implicitly.
So understanding how many ways you can form a tree with certain properties, like a specific height, gives insights into, well, into those applications.
Absolutely. It informs algorithm design, network topology analysis. It's foundational stuff, even if it sounds specific. Knowing the number of possibilities is often the first step.
Okay, so let's dig into the structure again.
Okay.
A rooted tree. You mentioned the root node. What else?
Well, you have the root. Then you have internal nodes. Those are nodes that have children branching off them. And then you have leaf nodes, the endpoints, which don't have any children.
Right, and the connections define that parent-child link.
Yes, and that's what defines the levels, or the depth. Root's depth 0, its children are depth 1, their children depth 2, and so on.
And the height of the whole tree is just the biggest depth value you find anywhere in that tree.
Correct. The maximum depth among all nodes. And for A000235, again, that maximum has to be 3.
I noticed our sources mention some figures like 5.2.1 and 5.2.2 in Mathematics LibreTexts, distinguishing free trees and rooted trees. What's the difference there?
Ah, good point. A free tree is just a connected graph with no cycles. Think of it as the underlying skeleton.
Yeah.
When you pick one node in that free tree and call it the root, then you get a rooted tree. You impose that hierarchy, that direction downwards from the root. The figures show how the same free tree can look different depending on which node you designate as the root.
Right, okay. So choosing the root changes the perspective, the depths, and potentially the height.
Exactly. Now for A000235, we're already given that it's a rooted tree and its height is exactly 3.
So that means the longest path, root to leaf, is precisely 3 steps, 3 edges. There might be shorter paths, right?
Oh, certainly. You could have branches that stop at depth 1 or 2, but there must be at least one path that goes all the way down to depth 3, and no path can go beyond depth 3.
Okay, that makes sense. Now, counting things like this, it brings up graph enumeration. One of our sources mentions labeled versus unlabeled trees. Which are we dealing with here?
Good question. For A000235, we're counting labeled rooted trees. That means each of the end nodes is considered unique, distinguishable.
So if you have the same tree structure but swap the labels on 2 nodes, you count that as a different tree.
Correct. If the nodes were unlabeled, we'd only care about the shape, the pattern of connections. But here, the identities of the nodes matter.
And the sources also mention generating functions as a tool for this kind of counting. Can you give us the quick version of what they are?
Yeah, the quick version. Well, imagine you have your sequence of counts, A1, A2, A3, and so on. A generating function basically encodes that entire sequence into a single function, usually a power series, where the sequence terms are the coefficients.
Okay, like a mathematical suitcase for the sequence.
That's a nice way to put it. And the magic is you can often manipulate these functions algebraically, add them, multiply them, differentiate them, and those operations correspond to combinatorial operations on the structures you're counting. It's a very powerful technique for finding formulas or relationships.
Right, so let's look directly at 000235 on the OEIS site. What does it tell us? The first few terms are listed.
Yes, it starts 0001388183876 That's for n equals 1, 2, 3, 4, and so on nodes.
And those initial zeros make sense now, right? You said you need at least 4 nodes for height 3.
Exactly. A root, a child, a grandchild, and a great-grandchild. That's the minimum chain, 4 nodes, 3 edges. You just can't do it with 1, 2, or 3 nodes.
Then there's this comment, 1, 1, 2, 3, 5, 8, convolved with 0, 0, 1, 2, 4, 7 equals 0, 0, 1, 3, 8. The first sequence is clearly Fibonacci A000045.
Right, and the second one, 001247, is A00000383, which the OEIS tells us counts rooted trees of height at most 2.
And the result of this convolution matches the start of our sequence, A000235. What does convolution mean here?
Convolution often pops up when you're combining structures. It suggests that maybe trees of height 3 can be built somehow by combining elements related to Fibonacci numbers and elements related to trees of height at most 2. The exact combinatorial reason for this specific convolution isn't immediately obvious from just the comment, but it's a strong hint of an underlying structure.
Interesting. There's also a formula, AN, A0000000141. We just saw A0000000041. We just saw A00000041. That's the number of partitions of n, or, well, partitions of n1 here.
Yes, A00000041 counts the number of ways to write n as a sum of positive integers. Partitions have known connections to counting certain types of unrestricted rooted trees. This formula looks like an inclusion-exclusion or subtraction principle.
So you take all the trees of height at most 2, that's A00001303, and you subtract something related to partitions, A000041n1, to somehow isolate just the ones with height exactly 3.
That seems to be the idea. You're starting with trees of height 0, 1, and 2, and trying to subtract off the ones that are not height 3. The exact role of the partition function A00000041 n1 in removing the height 0, 1, and maybe some aspect of height 2 counts would require digging into the proof behind that formula. It's not immediately obvious why partitions are the thing to subtract.
Okay. The OEIS entry also has code snippets, Maple, and Mathematica. What do they add?
They show that this isn't just theoretical. There are concrete algorithms to compute these numbers. You can run this code and generate the sequence terms yourself. It bridges the gap between the abstract math and actual computation.
And there's a cross-reference to A034781.
Right. That's apparently a table where rows are n, number of nodes, and columns are h, height. Our sequence A00000035 is just the column where h3, so it fits into a bigger picture of counting trees by height.
And finally, it mentions work by Riordan from 1960, and Sloan's program is based on that. So people have been working on counting trees by height for a long time.
Oh, yes. Riordan was a giant in combinatorial enumeration. His work laid the groundwork for a lot of this. The fact that it's referenced and implemented shows this is a well-established, important problem in the field.
Okay, theory and formulas are great, but let's try to picture these trees. The simplest one, NEA4. What does that look like?
The only way to get height 3 with 4 labeled nodes is a simple path. Root must child, my share, my child, great-grandchild, leaf. Just a line.
A chain of 4 nodes.
Okay.
And then for N5, how do we add the 5th node but keep the height exactly 3?
Right, you need to add that 5th node without creating a path longer than 3 edges. So you could attach it as another child of the root. Now you have one branch of length 3 and one of length 1.
Okay.
Or you could attach the 5th node as a child of the first node along the main chain, the one at depth 1. That node now has 2 children, one leading down the main path, the other being the new leaf at depth 2.
Ah, I see. Or even attach it as a child of the node at depth 2, making that node have 2 children, both leaves at depth 3.
Exactly. You can add branches, but you have to be careful not to extend any path beyond length 3. For N5, considering the different places you can attach the 5th node and remembering the nodes are labeled, you end up with the 3 distinct possibilities counted by a 5.
So it quickly becomes quite complex to track all the possibilities while sticking to that height rule.
It does. That's why having the sequence and the formulas from the OEIS is so useful. It gives us the precise answer derived from these combinatorial principles.
So wrapping up this deep dive, A000235 gives us a really specific count: rooted, labeled trees, n nodes, height exactly 3. But exploring it touches on a lot of core ideas.
It really does. Definitions of trees, height, labeled versus unlabeled counting, generating functions, connections to other sequences like Fibonacci and partitions. It's a nice microcosm.
We definitely encourage you, the listener, to check out A000235 on OEIS.org. Follow the links, look at the references, maybe even try running the code.
Yeah, see where it leads you. And think about where these ideas might connect to things you're studying or working on, especially in CS or math. These aren't just abstract numbers, they relate to how we structure information.
Absolutely. Getting comfortable with these kinds of combinatorial objects, like specific types of trees, really does unlock doors to understanding more complex graph theory and discrete math concepts.
And maybe it gets you thinking, what happens if you change the constraint? Height 4. Or maybe trees with a certain number of leaves. The OEIS is full of sequences born from asking those kinds of questions. What other properties could we count by, and what patterns would those counts reveal?